Okay, so let's start lecture 2. As I said, we'll come back to atoms in the tutorial later on this afternoon. And I may even, looking at the balance, I may take like more tutorial time, it's like less lecture time, and then balance a regular board time. We got people online? Just supplementation batteries of kids. Frankly, it's up. Tim, and I've run out of batteries already. Perhaps a battery, you know. Well, the more good way is past that. Okay, is that better? Right, okay, good. Let's go for it then. So this is the second. Come in, we're just starting, come in. This is the second topic, not the second lecture. Another one with bad batteries. Globally time. Subongal. Sudumpers. Is that better? Okay, thank you. So we're going to talk about molecular motions in general, which I already briefly talked about, and then rotational spectra. Rotational spectra have become, over the last 50 years, incredibly important in astronomical spectroscopy. And indeed, when I go to astrochemistry meetings, practically everyone else in the meeting is talking about temperature rotational spectra at 20 Kelvin, and I'm talking about exoplanet spectra at 2000 Kelvin, so there's a little bit of a mismatch. So there's a huge amount of work done on rotational spectroscopy. And I'm not going to survey the work, but I'll tell you what it is they're looking at. So I said this already before lunch. If you have n atoms in a molecule, you have 3n degrees of freedom, basically x, y, z for each atom. 3 of those degrees of freedom are translation of the whole molecule through space. It's a single unit. That's essentially a continuum spectrum. I mean, if you ignore things like walls in a room and quantize the energy levels that way, but basically it's a continuum spectrum. We're not interested in it, we ignore that. You then get 3n minus 6 internal coordinates, 3 of which represent rotations, except if the molecule is linear, in which case I normally have a linear molecule in my pocket. Here we are. So if you have a linear molecule, you can't rotate in this direction because there's no moment of inertia. So that you only have 2 degrees of rotation, that one and that one, you have an extra degree of vibration. And so you get 3n minus 6 vibrational modes in most cases, but 3n minus 5 in linear molecules. And if you take the obvious linear molecule case where n equals 2, 3n minus 6 means you get 1 vibrational mode. Sorry, 3n minus 5 means you get 1 vibrational mode. So for rotations, we have to start considering moments of inertia. And this is where you have to use principal axes. In principle, you can make a moment of inertia tensor and take the principal axes of these. But in practice, in nearly all cases, not in all cases, but in nearly all cases that you deal with, at least for small molecules, it's pretty obvious where the principal axes are. And I already said for my pseudo-linear molecule, you have an axis here, you have an axis here, and it doesn't actually matter anywhere around there where you take the axis. And then you have a unique axis along here, which has no moment of inertia. Similarly, if you take a symmetric top system, it's pretty obvious you're going to have an axis down here, and then you have 2 axes here. It doesn't matter how you take them. If you have a spherical top, which you can think of as a football, you have 3 axes. It doesn't matter bait them. They just have to be orthogonal to each other. You get all the same answers. Life gets interesting when you get an asymmetric top, which has 3 different axes, one here, one here, and one here. And again, in this, it's obvious. If you have a very complicated asymmetric top, and I'm looking for a good example in the room here and failing, probably that camera stand. it's not going to be obvious where you take the axes, and then you have to start doing moments of inertia. So if you get big molecules, proteins, biomolecules, then you actually have to do it seriously. Take the moments of inertia, diagonalize it, and get your principal axes. But even that is not particularly difficult, particularly today. I'm sure there are computer programs that will do it for you in seconds. So basically you want 3 axes. And there's a convention that you label the moments of inertia of the 3 axes, A, B, and C, capital letters. And the A-axis is the one with the smallest moment of inertia. The B-axis is the intermediate, and the C-axis has the largest moment of inertia. However, as we'll come to in a minute, notice these are not just greater than signs, they're greater than equal signs, because in several cases, the moments of inertia are equal to each other. And you have a thing called the rotational constant, which when you only have one of them is always called B. When you have 3 of them, they're called A, B, and C, and variance on N, and we'll come to that in a minute. And they're inversely proportional to the moment of inertia. They actually have this very simple relationship, Planck's constant divided by 2 pi squared, divided by twice the moment of inertia. So you should remember this, it's very simple. And obviously, as they're their inverse relationship to the moment of inertia, you now get that C is less than B is less than A. So A is the biggest axis with the biggest rotational constant, the smallest moment of inertia. So to get a rotational spectrum, your system has to have a dipole. A dipole basically means an asymmetry. So my quasi-linear molecule here has a dipole because it's got this asymmetry of having a cap on one end and not on the other end. So the charge distribution, if this was a molecule, would not be symmetric. You get a dipole. If you get a molecule like hydrogen, which is symmetric, there's no dipole. So you don't get a rotational spectrum. Let's rephrase that. You don't get a dipole allowed rotational spectrum. And these have the selection rules, delta J is plus or minus 1, and 0 for asymmetric tops, but basically plus or minus 1 will come to 0 in a bit. The intensity is simply proportional to the square of the dipole. So you can look at a molecule, if you know its dipole moment, you'll know very quickly how intense it is. If you get molecules like the famous salt, sodium chloride, ionic molecule, Na plus Cl minus, very large dipole. Basically, the dipole in atomic units is equivalent to the bond length. Very large, strong rotational spectrum. Easily observed in interstellar medium. It's a huge dipole. You don't need very much. You just need a little pinch of salt, and you can see it. Other molecules have small dipoles that are more difficult to see. From a quantum mechanical point of view, the rotational spectrum is slightly unusual. You can write down a complete basis for any J level, and it's finite. So normally if you do, and we'll consider vibrational motion, we already considered electronic motion. If you remember, there were an infinite number of electronic band states in your atom, and then you've got the continuum on top of it. So you've got a countable infinity and then an uncountable infinity above it. So you can't use a finite basis to represent that. You need a very complicated basis. Here, if you've got J equals 3, there are precisely 7 basis functions, 2J plus 1 of them, and that gives a complete basis. So this is it's property of angular problems, but it's not a general property. It's a very useful property. If you solve the problem, you know you're going to get the right answer. You completely converged it. In the absence of a so that's 2J plus 1 in the absence of magnetic field, you get another 2J plus 1 degenerate levels for each of them. Basically, you get 2J plus 1 in the molecule frame and a second 2J plus 1 in the lab frame. If you don't have any external fields, the lab frame ones remain degenerate. If you put in a field, then you start splitting those, so you get an extra 2J plus 1. There's a parity here, which is by convention called a Wang parity. I assume a gentleman called Wang or a woman called Wang designed this parity. Basically, it splits the basis into j+1 functions, j functions, and they're the O and even functions that we talked about already with atoms this morning. So if you're actually addressing a problem, you don't even need to do 2j+1. You do one problem with j+1 and one problem with j, and that will solve it. So I already mentioned you get 4 types of rotors. You get a linear molecule where the smallest moment of inertia is 0. And then the other 2 moments of inertia, which are conventionally called B, are equal to each other. So that's our B and C moment of inertia here, and then 0 along the axis. That's a linear molecule. You get spherical tops, where all the moments of inertia are equal to each other. Basically, you just need 2 axes bigger than, 2 rotation axes bigger than, let's get this right. Yes, you need at least one axis bigger than a 2-fold axis, and then a second rotation axis, and that will give you a spherical top. And I'm going to give you some examples of molecules that satisfy each of these in a second. And then you get symmetric tops like this, and you get 2 types of them, prolate and oblate. And I've got a picture of those I'll show you in a second. Basically, oblate is flat and prolate is long and thin. And then a lot of molecules are asymmetric tops, where all the different axes are different. And they have different rotational structures. Very simple, simple, extremely complicated, basically. So to give you some examples, linear molecules, anything diatomic, obviously. So H2 and CO, but there's a whole bunch of polyatomic linear molecules, CO2, HCN, acetylene. Actually, astronomically, a whole series of molecules, HCN, sorry, I should write it. When you say N, it's ambiguous. I'm going to have 2 N's and they're going to be different things. What do I do with the pen? I've put it back there, yep. You have a whole bunch of molecules like that, where you have a long linear chain of carbons. N goes 3, well, HCN is the first one, then 3, 5, 7, 11, I think up to 13 has been seen. And they're all linear, and they have a nice strong dipole, because you get a charge separation between the hydrogen and the nitrogen. As you put another 2 carbon atoms in, they get less of them, but the dipole gets stronger, so you can still see them because the charge separation gets bigger. So that's a classic astronomical linear molecule that's easy to see. I need to do it instead. Spherical tops, methane, very important molecule. Spent a lot of my time worrying about methane. And carbon-60 buckyballs, also a spherical top. There are other examples, silanes, SiH4, SF6, but they're 2 good astronomical advantages. Symmetric tops, H3+, flat. So, and it's equilateral triangle, so in the plane, all the moments of inertia are the same. Perpendicular, it's a different moment of inertia. Anyone here ever heard of something called the laminar rule for moments of inertia? I have a nod. Anyone else nodding? It's funny, I did this at school. I did this at school, but none of our undergraduates ever heard of it. It's interesting. So the laminar rule says basically, if you do it. Yeah. So come on, be a bit more responsive here, people. Can I try again? Who's heard of the laminar rule? Please put your hands up if you've heard the laminar rule. I'm still only seeing 1 hand, 2 hands. Anyone else? 3, 4, 5 of you. Okay, a few of you heard of it. Basically, the laminar rule is quite simple. It says if you have a planar system, the moment of inertia there and the moment of inertia there, the third one in the plane is the sum of the other 2 moments of inertia. So for H3+, you've got okay, it's not this shape, but you've got a planar system, 2 moments of inertia. In the case of H3+, because of the symmetry, they're all the same. The C moment of inertia, the biggest one is the A. The A moment of inertia is the is the sum of the two, and it's in the plane going perpendicular to it. Other examples of symmetric tops are ammonia, phosphine, chloromethane. These all have threefold axes down here. Okay? Asymmetric tops, lots of them. So I've given you a few examples: water, formaldehyde, ethane. Give you that one for a very specific reason we'll come to in a second. Now, I said to have a rotational spectrum, you need to have a dipole. So we're now going to say which of these have dipoles. Fine. So we need to go through again and say which of these have dipoles. So for linear molecules, some do and some don't. Carbon monoxide famously does. It's, as I already said to you this morning, hugely monitored in the interstellar medium. It actually has a very small dipole. It has a slightly unusual property that its dipole moment changes sign very near the equilibrium, which means the average dipole is actually very, very small, but it's finite, and there's a lot of it out there, so it's very easy to see. H2, CO2, and acetylene, are all symmetric molecules, so none of them have permanent dipoles. But HCN has a pretty large dipole, as done the molecules I wrote up and scrubbed off. Symmetric tops do not have a dipole. It is not possible to design a symmetric top and have a dipole. A dipole means some unique direction, and we've already discussed that symmetric tops are like footballs, they're completely spherical. However, there are observed rotational spectra of methane. They're pretty weak. What happens actually is if you spin the molecule hard enough around one axis, it distorts slightly. I did one of my students, she did a PhD exam just recently, did a big project collecting all the known energy levels of methane, and it turns out that in the 1980s, measuring one rotational line of methane was enough to get you a phys rev letter in the publication. So it's doable, but it's fairly unusual. So symmetric tops. Where's my picture here? Oh, maybe I've lost my picture. I had a picture of a cigar and a frisbee. So oblate is flat. It's a frisbee. Prolate is a cigar-shaped object. So H3 plus planar doesn't have a dipole. As soon as you're not planar, you'll have a permanent dipole moment. Ammonia has quite a strong one. Phosphine, CH3Cl will have dipoles. In general, asymmetric tops have dipoles. They don't have much symmetry, but I deliberately put C2H4, which looks like this. So it's a planar molecule looking like this. It has one symmetry axis there, one symmetry axis there, one symmetry axis there. D2H symmetry. You can rotate it by 2 in every direction. It cannot have a dipole, or it wouldn't have that symmetry. So this is rather unusual, but it is possible to have an asymmetric top and still no dipole moment. Right. This is where I get you to do some work. I'm going to start at the back row. I'm going to be cruel because the first one is quite difficult. But if you don't know the structure, I'll draw it for you. Let's just clean this. There we are. Okay. So lady in the yellow at the left, ozone. Looks like that. It is not an equal, it's a symmetric triangle, not an equilateral triangle. Any idea what sort of rotor it is? Nope. If it was an equilateral triangle, it would be a symmetric top, but it's not. It's a bent. So if you have a moment of inertia here and a moment of inertia there, they're not equal to each other. So, any ideas? Asymmetric top. Okay, so this is asymmetric. All right. Person next to you, do you think it has a dipole or not? No, it has a dipole because it's not symmetric. The three distances are different. So it has a dipole actually in this direction. In the plane, obviously, there's no dipole, and there's a symmetry that way. So it has a dipole pointing in that direction. Okay. N to O. Where are we? Gentleman with the beard there at the back. You can write this like that. Any ideas? I could be more explicit, but I'd tell you the answer is linear. So, what sort of molecule is it? Rota, is it? Linear, right? Does it have a dipole? Just says something on the front here. You will have it done.
Why, David?
Sorry?
Why, David? Hawkins?
Everything's 180. It's a linear molecule. It's interesting. This molecule gets incredibly little attention. It's about fifth most common in the Earth's atmosphere, fifth or sixth. But no one seems to worry about it. It's a linear molecule. You think it has a permanent dipole? I'm getting nods up the front here, if you want a clue. So this has a dipole. If it was NON, linear molecule, symmetric, it wouldn't have a dipole. But it's not. It's like that. Okay? Gentleman in the face mask, NO2. I'll give you a clue. NO2 is not linear. It looks like this. What do you think that is? Asymmetric, right? Coming to the lady and sitting in front of you. Do you think it has a dipole or not? NO2? It should have, right, good. So this is the same as ozone, symmetric with a dipole. So they're both the same. Right, silane, SiH4. I already said that, if someone was really listening. So gentleman there in the grey shirt, SiH4. Symmetric, right? Does the symmetric top have a dipole? Sorry?
It can have a stop. No.
Yes. Symmetric top.
Symmetric top.
Symmetric top is the same everywhere. You don't.
Symmetric. Not symmetric.
You don't. If you have a football, it's completely spherical. This is like that, so there's no dipole.
So similar to methane, right?
Yeah, similar. This is basically like methane. The same structures meet.
Yes.
So symmetric top, no dipole. Okay. NO. Where have we got to in the back row? Gentleman there. Yeah, dipole or no dipole?
It's as a dipole.
Yep, good.
Where do you want to guess it's a linear?
Linear dipoles. Next to it, O2. Jasmeet. Yeah, linear, no dipole.
Then I got yes. Pop.
SO2. has that structure. Where are we?
Subpattern.
The Virginless and the effectress.
That's me.
SO2, what do you think it is? As the rotor goes. Yes, you.
So it's like salt to cook. That was not prevalent. It's on the top of the TV show, is it? Screw that. Huh? You took the story? I saw it, yeah.
It's, yeah. SO2. Yeah, what do you do? Asymmetric top, very good. Lady next to you, do you think it has a dipole or not?
Or waves and pieces like what we used.
Has a dipole, yeah. So this is the same as C2H4, benzene. There's a good one. Excellent molecule. Symmetric top, yep. Oblate or prolate? There's a different, harder one. The oblate is the pancake-shaped one. Prolate is the cigar-shaped one. No, I didn't ask you that question. I said, which sort of symmetric top is it? Is it very long and thin, or is it flat? Yeah. So it's basically planar, isn't it? So it's a flat one. So it's an oblate symmetric top. Okay. Dipole or no dipole? In benzene.
That can almost end.
50-50, I'm afraid you got it wrong. It's very symmetric in a plane. So it has a six-fold symmetry in the plane. I mean, it looks like... conventionally drawn like that with a ring, but what that means is there's a hydrogen hanging off each of these. It's rather more symmetric than my drawing. Every carbon is in the same position, every hydrogen is in the same position. So there's no dipole. Okay. This thing is in the way. What have I got underneath there? Yeah, okay. Yeah, there we are. Thank you. Come on, move a bit more. What did I do to move it, Bobby? Cancel. There we are. So this is symmetric, no dipole. I've got an easy one for if anyone's been awake. Gentleman there in the shirt. Ethylene, C2H4. We already had that one on the last slide. Yeah. Do you know what sort of... In fact, I had a picture of its structure. I can draw it again. Looks like that. Sorry? I think I was making the right answer, but I can't quite hear it. Yep, that's right. Has it got a dipole or not? No dipole, that's right. So, acetylene. I think I had that one before as well, actually. Acetylene, gentleman there. No, your turn. Linear, dipole or no dipole? No dipole, that's right. SO3. SO3 is slightly beyond my planar drawing. It looks like that. It's a pyramid.
Back.
Okay. Any idea what's it? What sort of top it is?
Top shape. You know what the NS we have the C?
Yeah. Yeah, it's a symmetric top.
Dipole
Upole or no dipole?
It's then this is down.
Has
Dipole.
a dipole, yeah, because if it was planar, it wouldn't have a dipole, but I think it's not planar. Okay, it's a pyramid. Yep. Yes, that's a good question. I actually don't instantly know the answer. Even having done a line list for it, I probably did when we did a line list 10 years ago. It depends. I mean, for some molecules, it's very obvious. But other cases, you actually have to take the moments of inertia. The question is the moment of inertia that way bigger or smaller than the ones that way? And to be honest, without knowing the bond angle here, I it depends on the bond angle here. So I don't know the answer off the top of my head. Okay.
But to look at which direction is heading along above it, depending on that certain data.
Lady in the white shirt there. CS2. I will give a picture of it.
There is the one involved in the sink that has.
Looks like that. If you compare, it's basically an analog of the carbon dioxide. Linear molecule, right? Does it have a dipole? No. Okay. Front rows, I'll come back to you next time. I've got some. You won't get there quite simply. But well done, everyone. So that's just to give you an idea of how you classify them and look for dipoles. Obviously, you do need to know some information about the structure, which, if you're not a chemist, you may not instantly know, but it's normally there on the net if you need to look it up. Right. I'm going to go through actually what the rotational spectra of each of these look like, but first I'm going to do a little bit more on the properties. No, I need to do this first, you know. There we are. So two side issues. The second one is a bit of a niche thing, but happens to be rather important for astronomy. The first is general. So rotational motion always goes around the center of mass. So when you're rotating something, when you consider its rotational motion, you have to decide roughly where the center of mass is, and that's what you're rotating about. And that sort of comes with the way you define the coordinates, because the translational motion is around the center of mass, so you've already fixed everything at the center of mass at that point. Okay? There's a general theory that if you have multiple moments, so charge is the leading multiple moment, dipole, quadrupole, in principle octopoles, I'm not going to consider octopoles, but as you go down, only the first one is invariant to the center of mass. So if you have a non-charged system, and apart from H3+, all the other systems on my last page were non-charged, the dipole doesn't shift if you change the center of mass. If you have a charged system, it does. It affects the center of mass, and that's important when you consider things like H2 and H2+ and HD+. Because H2 is symmetric, has no dipole. HD, within the Born-Oppenheimer approximation, still has no dipole, because the dipole is independent of the center of mass. The fact you move the center of mass doesn't matter. It has an incredibly weak non-Born-Oppenheimer dipole, but it's effectively the same effect as the quadrupole. HD+, conversely, you've shifted the center of dipole, the center of mass. So the vector of charge is still the middle of the molecule. The center of mass is shifted nearer the deuteron than the hydrogen, because the proton is lighter. So you end up with quite a sizable dipole as a result, and gives a HD+ has a strong rotational spectrum. HD does not. H2 does not. And it's purely a effect of the charge. Now, interesting for H3+, you get exactly the same. So H3+ is known in the interstellar medium to basically promote all the reactions. I mean, the very simple sort of mechanism that starts off with forming molecules in the interstellar medium from nothing is you have a load of hydrogen. A cosmic ray comes in, ionizes the hydrogen, gives you H2+. H2+ collides with H2, and basically at every collision forms H2+ and a hydrogen atom. That's a very exothermic reaction. It's a very efficient reaction. There are no barriers to it. So you get H3+, and H3+ then is a very reactive species and starts the chemistry chain. So it'll protonate things, protonate atoms, protonate other molecules, etc. There was a huge search 40 years ago now for H3+ in stellar medium. It's incredibly difficult to see. You can't see the rotational spectrum. People have now seen it against starlight. So if you look at a line, a site which has a star against it, you can see the vibrational spectrum and absorption. There's still no one has seen any rotational spectrum H3+. I've calculated what it should look like, but no one has seen it. H2D plus and D2H plus both observed interstellar molecules and seen relatively easily, despite the fact that the abundance of deuterium to hydrogen is about 1 part in 10 to the 5. You get slightly above that from something called fractionation, which I'll deal with when we look at vibrational spectra. But it's still, this is the trace species. And the reason is simply that if you have D2H plus, or H2D plus, the center of mass is here, which is where the center of charge is. Sorry, let's start again. The center of charge is here, the center of mass is halfway along that line, and it's a relatively simple bit of geometry to work out the difference between them. In an atomic unit, the dipole is simply the distance between those 2 points. Because it's ER, the dipole is E times R. E is 1 in atomic units, and R is that distance in Bohr. So it gives you the dipole in atomic units, and dipoles are normally given in debye, which is a strange unit because it doesn't relate to anything. But atomic unit is 2.54 times 1 debye unit. So this H2D plus has a dipole of about less than half an atomic unit, but sorry, less than half debye, about 0.4, 0.3 of a debye. But that's way bigger than CO, for instance, it's about 0.1 of a debye. So it has a nice atomic unit. So that's a important consideration if you're looking for these things. And we've just classified them all. But then in some cases, if you put an isotope in here, you're going to change, well, quite often you're going to change the classification, because you can take something which is a symmetric top and it becomes an spherical top and it becomes a symmetric top. Symmetric top becomes an asymmetric top just by changing the isotope. But here you also dramatically change the dipole. So here we have, this is 1.65, and it's relatively easy. You can go and work it out yourself to work out what that distance is, purely in terms of geometry, with the knowledge this is a triangle where each of the sides are 1.65 atomic units. It should take you all 5 minutes for the pencil and paper and not even a calculator. Right. So what do the spectra of these molecules look like? Oh, sorry, I've gone on and I forgot to do, no, not that. Yes, somehow. So I'm going to start off with what's called the rigid rotor approximation. And that says basically, as you rotate the molecule, it doesn't distort. It's not a completely correct approximation, but as you'll see, it's a very good starting point. To qualitatively understand the spectrum, it's a completely sufficient starting point. If you want to do detailed numerical studies, you have to go beyond that. But actually to get a visual image of what the spectra look like, that's enough. So I'm going to go through the different types of spectra within the rigid rotor approximation. So there's a very simple formula for the rotational energy levels of both a spherical top and the linear molecule. They depend that both of them only have one rotational constant B, and the energy levels depend on J plus 1 times B. So just to remind you, J is the rotational angular momentum, nothing to do with the J we talked about this morning, which is the total angular momentum of the atom, though it is sort of the total angular momentum of the molecule. We'll get to that. B is the rotational constant, which depends on the moment of inertia, and I seem to have left a 2 out of this formula. My apologies. If you're writing it down, it should have a 2 there, so it should be 1 h cross squared upon 2I, or I2 as I've written it rather inelegantly. I is the moment of inertia. So for a linear molecule, it's just the reduced mass times the distance between the atoms. That's not quite the formula for the spherical top, but it's something along those lines. I haven't worked it out And this formula depends linearly, or in fact inversely, on the moment of inertia. So if you change, say, hydrogen for deuterium, you're going to get a big shift. I didn't talk about isotopes when I talked about atoms this morning, because for nearly all atoms, deuterium and hydrogen being the honorable exception, you cannot see the isotopes. The lines just lie on top of each other. They don't lie absolutely on top of each other, but to within any resolution that you're likely to get in an astronomical spectrum, they lie on top of each other. It is really difficult to get isotopes using atomic spectra. If you want really easy isotopes, you go for the rotations because of this property. And isotopes are a really important handle on nuclear processes in stars. Because there are, I think everyone in the room knows that beyond hydrogen and helium, basically matter comes from stellar processing, that you create carbon and other nitrogen, oxygen, etc. in stars, maybe supernova explosion to get the heavy metals and things like this. But actually, there are several different processes that depends on things like the mass of the star. And if you want to understand those processes, you need to understand isotopes. I'll give you a very simple example. The abundance of carbon-13 on Earth is about 1%. Slightly less. There are bits of the universe where it gets up to a third. And that's because it's been made in a completely different process to the way the carbon was made on Earth. And you can only tell that if you know the isotopes. And basically, rotational spectra, you can do it with vibrational spectra as well, but rotational spectra is really the easiest way of knowing the isotopes. So this business about changes in reduced masses is important. Now, in practice, it's not quite true to say molecules are rigid. There are at least two other effects you need to consider. They vibrate, and we're going to come to that in the next series of lectures. And I put this R as a constant. It's actually an expectation value of the bond length as the molecule vibrates. So as you change the vibrational state of the molecule, that expectation value changes. In general, the rotational constant gets slightly smaller because the expectation value of the distance gets slightly longer, but that effect is very small. And you'll see in the spectrum that when we do vibrational spectra, if you make the assumption that the rotational constant in the ground state and the vibrationally excited state are the same, you get a very good image of what the spectrum looks like. It's not perfect, but it's very good. We do that for electronic spectra, it doesn't work at all. Because the electronic spectra, the B's change dramatically. So you must, if you're doing it, actually consider vibrational motion. The other thing is called centrifugal distortion. And my way of thinking of that is if you have two balls on a spring and you wave it around your head so that the two balls rotate faster around your head, that spring will stretch because of the angular momentum. And that's exactly what happens with the molecule. You can think of the binding, when you're doing rotation and vibration spectra, you can think of the binding of the molecule as a big stiff spring holding the two atoms together. So if you wave that thing around faster and faster, you stretch more and more, and you get a centrifugal distortion effect. That depends, as I'll show you. So this depends on J squared, roughly, Jj plus 1. The centrifugal distortion depends on J squared, J plus 1 squared, in other words, J to the 4th, approximately. And it lowers the energies. It takes the energies down. I'll come back to that in a bit. Temperature effect. Normally, those of you who've done Boltzmann statistics or anything, no matter what the temperature is, the ground state is the most occupied level. It's not true for rotations. And it's not true for rotations because you have this degeneracy factor. I already said to you that each rotational level in the absence of a magnetic field is 2J plus 1 degenerate. So because of this factor, the most populated rotational level of a molecule at a finite temperature, 0 is always going to be the ground state, but at a finite temperature is generally not the ground state. Just to give you a concrete example, for water vapor in the room here, the most populated energy level is J equals 7. And you only get that by doing the maths and working it out. So you need nearest down at 300 Kelvin in this room at the moment, and the rotational constants for water, but it turns out J equals 7 is the most populated level. So to get the thermal population, you need to consider a Boltzmann distribution. Am I safe in expecting that everyone's met Boltzmann distributions before? Yep, good. So the energy, if you just keep rigid rotors, and frankly for doing this it's good enough just to keep rigid rotors, it's Bjj plus 1 divided by Kt divided by the partition function with the degeneracy 2j plus 1, and the partition function is simply the sum over all the energy levels. So you can get that, and you get the degeneracy, and you get an extra term in the degeneracy to do with nuclear spin, Gn. As I said, I'll probably come back to that later on when we're doing the vibrations. So Gn gives you a nuclear spin, which is if you had one, a molecule, say CO is not a good example. CO, neither carbon 12 or oxygen 16 have they're both spin 0, so Gn is 1 in that case. What's a better example? NO, nitrogen has nuclear spin 1, oxygen has 0. So in that case, you get a factor of 3 from 2i plus 1 in that, and it should be statistical, not statistical. It generally cancels out in most things. So in general, the most populated level is given by this formula, half the square root of Kt upon B. You have to get Kt and B in the same units. And the easiest way of doing that, this is not a new problem to use, the easiest way of doing that is something called the second radiation constant. C2, and don't use my off the top of my head number. Get the units the right way up. Centimeters minus 1, Kelvin minus 1. If you do that, then you can use temperature in Kelvin and rotational constant in wave numbers. Look this up, it's a standard constant. And so it's just a way of giving Boltzmann's constant in wave numbers, but it's called the second radiation constant. And it allows you to use this formula without having to do any units conversions. So you can get the temperature very simply. And if you do that, you can show, and a little exercise for you to do, just take this and differentiate it and set it to 0 so you get the maximum value. You will find that the level with the greatest population is given by this formula. So the rotational spectra of diatomic molecules are beautifully simple. It's also true of linear polyatomic molecules. So they're simply like a comb. And you can see, you could fit the whole spectrum and get a temperature. You could just say, oh, if this is an absorption spectrum, the lowest state here is 3, so J equals 3 is the most populated level, and stick it in the formula. And this number here is actually twice the rotational constant. It's 2b if you don't have any distortions. And I didn't derive it, but if you take J plus 1 and then add J on it, and you get J plus 1 times J plus 2 and difference them, you end up just finding that it's 2bj is spacing. So each level goes up by 2b. So 0 to 1 is at 2b, 1 to 2 is at 4b, 3 to 2 is at 6b. They just go up as 2bj going through the molecule. So you can look at that. You can read the rotational constant off here. It's 0.1 megahertz. You can put the numbers on them, and even if you're missing a few, you can still do it. It's very easy. They're very easy to analyze. Sorry? Okay, good. I will show you one more picture. Right, okay, so I put this down, the thermal population given by that. Rotational constant is 2b equals 100 megahertz, so the rotational constant is 50 megahertz. So here we have a picture, and I've got a random CH plus line in there, but the rest of it is just one molecule, and we'll discuss what it may or may not be after the coffee break. Before we go to coffee, any questions? Sorry? We have 10 minutes. Oh, I thought you said we had 5. He came late. He's double dipping at both ends. Okay, well, if you look at this, the gap between the lines, so that's just below 600 to just below 800. It's about, these are slightly more than 100 gigahertz, no, not megahertz, between the gaps. So you've got one here, you're missing, I think, one line here. So you're missing 0 to 1. This is 2 to 1, 3 to 2, 4 to 3. You have, if you look at several of these, there are double lines. Anyone got any ideas what the other extra line might be? Suggestions? Yeah. I think I heard the right answers. I don't know who said it. Say it again. It's fine structured because of what? It's not fine structured. I don't think you could get fine structured like this due to having an open shell system. That is true. And it would look a bit like this. I don't think it actually is fine structure. So NO, for instance, which I talked about, is an open shell system. We'll have slight doublet structures like this. But I haven't done the rotational spectrum of fine open shell systems. I will briefly mention at the end of next lecture. Any other possibilities? Fine structure is indeed a possibility. I don't think this is the answer. Sorry, I'm going the wrong way. So what did we talk about here? Isotopes. So you get a small shift in the mass. So you go, say, from carbon, oxygen 16 to oxygen 17. You get a small shift in the moment of inertia. And it gives you these extra lines. Repeat?
We discussed the atomic spectrum, but it was too close to.
Yeah. So this is a relatively low resolution spectra. I'll show you after the coffee break some high resolution spectra. You will get spectral regions looking like this, with the whole thing spread out. But this is nice because you can see the structure. In fact, when I originally wrote the book, my edition 1 has one non-astronomical spectrum in, and it's the rotational spectrum of CO, because all the rotational spectra of CO that I knew from astronomy only had one line. And then someone published a very nice overview spectrum like this, maybe this one. And second edition, I replaced it in the book and got rid of my last lab spectrum. So there it is, what you assigned. And I think the small shadow lines here and here are carbon-13. You can see you're going all the way up to J equals 12, and it actually isn't particularly getting weaker. So this is a reasonably warm source. I couldn't by eye tell you where the maximum of those lines are. And this may not be thermodynamic equilibrium, and most interstellar medium is not in thermodynamic equilibrium. This is observation. Yeah. I said what it was. I think this is a galaxy. I'm not sure.
Sure about which one is the highest?
Yeah. So these are meant to be the same spectrum. It's just a slightly bigger scale. Which one's got the assignments on it?
because it's the and
Yep.
so it's 13CO, so you can have the oxygen as well.
You can also have the oxygen. 13 is more common.
Is it visible? No.
Yeah, I think with these,
I think this feature there is 30.
so it should be slightly.
The oxygen one you can't see it here.
Well, I think you think all the isotope got to CO, even things like 13 CO, oxygen 17.
So yeah,
But you just need better resolution
better resolution.
because this is we're going across
Yeah, it's very high.
100 gigahertz there.
You have to
Cut off in the span, that's 2 megahertz.
yeah.
So this is a nice didactic point of view. So if you see the whole spectrum,
Yeah.
but I will show some actual demo in Spectra, I'll say later on. They're very, very, very high resolution. I think the ones I've got aren't even state of the art. They're to use, so they're just things they're seeing. In fact, when you look at ALMA spectrum, you get something called the confusion limit. The confusion limit is not defined as the end of one of my lectures. The confusion limit is when everything is lines. So there's no background, it's all lines. So you obviously get weaker and weaker lines, partly because they're intrinsically weaker, but more because you get more and more trace molecules that have lines. Particularly, I mean, there's a classic problem with methanol, which has a very complex, it's an asymmetric top, strong spectrum, quite complicated. Then you get isotopes of methanol, which then have all these lines. It has low line vibrational states. There's an OH bond that can go down very quickly. So you get vibrationally excited states, they have lines. The whole spectra get littered with what are called weeds, which are methanol lines you don't want to know about because you already knew that methanol was there. So you get lines upon lines upon lines. Going back to stellar spectrum, Peter Bernard, who's a good friend of mine, you worked in this sort of area for a while, Bobby, has a satellite that's been going, just coming up to its 20th anniversary. It was meant to fly for 5 years, I think, originally, which is called ACE, Atmospheric Chemistry Experiment, and is essentially doing an exoplanet type observation of the Earth. So the Earth's here, and it peaks through the Earth at the sun. So it actually starts with a pure sun spectrum, goes down through the atmosphere until it gets blocked by the Earth, and then it goes back up the top and does another one. And it just does that 24 hours a day, nearly 20 years. The top spectrum is just the solar spectrum. This is an infrared satellite. We have the most superb infrared solar spectrum. At some point, they published a spectrum which had 250,000 observations of the sun, all aggregated together. They probably got more like 2 million or 2.5 million by now. That was completely the confusion limit as well. Totally features due to atomic and molecular species. When you look that deeply, it's just bumps and lumps and dumps, whatever, going through it. So these spectra are very rich. And when you come to the ALMA spectra, there's still large numbers of lines which get labeled U, and U just means undefined. They know it's a line, but they don't know what it is. And there's a whole area of people who go fishing in these. They dream up a molecule, either compute the spectrum or measure the spectrum, or compute the spectrum and they get a friend to measure the spectrum, and then they go looking for it in the ALMA thing, and then they publish, whoopee, we found this strange obscure molecule. And if it's something that people have heard of, like sugar, you get into Nature. And if it's a more obscure molecule, you get into astronomical journals. So anyway, that's a slight diversion before tea time. Let's have a break. I'll repeat on centrifugal distortion and things after when we come back again. Sorry, any other questions before we? Nope. Okay. Time for some chai.
Yes.